Now that we've added the ratio and root test to our arsenal, let's return to the topic of power series, and in particular the fundamental question that I posed 2 lectures ago, which was, given a power series, sum Cn, x minus a to the n, for what values of x does this series converge? I.e., if we consider the power series to be a machine, what values of x can I input into this machine so that I get a sensible output, i.e. a number? Okay, so we could think about x going in to the power series machine and outputting some Cn x minus a to the n. Okay, so before we tackle this question, let's recall the following important theorems and definitions from 2 lectures ago, or 1 lecture ago. Okay, so here are the theorem and definitions pertaining to the radius of convergence and interval of convergence. So at this point in the video, just pause and refamiliarize yourself with them, make sure you understand them, before we move on to looking at some examples where we're going to show how to apply the ratio test to determine radius of convergence. Okay, so here's the first example. Sum n equals 0 to infinity, x minus 1 to the n, over 3 to the n times n plus 1 cubed. And we're asked to use the ratio test to determine the radius of convergence for this series. So firstly, I want to recall the ratio test. Okay, and remember, the ratio test was written in terms of a series, not a power series. So when you're applying it to a power series, you have to think of x as fixed and as the x minus a to the n as being part of the a to the n. So the ratio test, if sum an is a series, consider L defined to be limit n goes to infinity, absolute value of an plus 1 over an, if, first option, L is less than 1, then the series sum an converges absolutely. Second option, if L is greater than 1, then sum an diverges. Option 3, if L equals 1, then the ratio test is inconclusive. Okay, so let's consider applying this to this example. Now remember, we have to think of x as being fixed. So for fixed x, okay, because you want to think of the x minus a to the n as being part of the an. So here our an is the entire piece, the x minus 1 to the n over 3 to the n plus 1 cubed. So then, following this formula, what's an plus 1? Well, everywhere we have an n, we just replace it with n plus 1. So we get x minus 1 to the n plus 1 over 3 to the n plus 1, open brackets, and n plus 1 is n plus 2. Okay, so L is going to be the limit, as n goes to infinity, of an plus 1 over an. Now remember, if you're dividing by a fraction, it's the same as flipping it and multiplying by it. So we're going to have x minus 1 to the n plus 1 over 3 to the n plus 1 times n plus 2 cubed times, and now flip an. So 3 to the n plus 1 cubed over x minus 1 to the n. So we get the following cancellations, the x to the n plus 1 and the x minus 1 to the n plus 1 and the x minus 1 to the n, and the 3 to the n with the 3 to the n plus 1. And we're left with x minus 1 over 3 times n plus 1 over n plus 2, and I bring them both inside the cube. And this just leaves us with x minus 1 over 3, as the cubed piece just limits to 1. So if we want L to be less than 1, then this is exactly the same as absolute value of x minus 1 being less than 3. So that tells you the radius of convergence around 1 is 3. Okay, so that's the first part of the question answered. Okay, so moving on to part B and part C. Part B, what are the values of x at the endpoints of the interval of convergence? So remember, this was the condition, absolute value of x minus 1 less than 3. If we were to draw that, this is centered at 1, and it means we can go 3 either side. So we can go to the right up to 4, and we can go to the left down to minus 2. Okay, and that's it. That's the two endpoints. So x equals minus 2, and x equals 4. And remember, you have to test these 2 points individually because the ratio test will give you that L equals 1 if you were to plug these two values in. And we know that that's inconclusive, so we have to test it individually. Part C, write down the series you would have to check for these tests. So fill in minus 2, fill in 4, and look at the series. So x is minus 2. Let's fill that in. Sum n equals 0 to infinity. Minus 3, minus 2 minus 1 is minus 3. 3 to the n plus 1 cubed equals, we can break up the minus 3 to the n as minus 1 to the n times 3 to the n. And of course then the 3 to the n's cancel. And we're just left with sum n equals 0 to infinity minus 1 to the n times 1 over n plus 1 cubed. Okay, let's look at the x to the 4, or x equals 4 case. So then we're going to get sum, and instead of minus 3 to the n, we'll just get 3 to the n over 3 to the n plus 1 cubed. And similarly, we just cancel the 3 to the n's, and we're going to get sum n goes from 0 to infinity of 1 over n plus 1 cubed. Okay, now we haven't yet developed the tools to decide whether these two series converge or diverge, but we'll develop the tools in a later lecture. Okay, so the next example is a very famous, very important power series. It is the sum n goes from 0 to infinity, x to the n over n factorial. Okay, so we're asked to find the radius and interval of convergence of this power series. So, as before, let's just define L. This will be the limit, as n goes to infinity, of the absolute value of an plus 1 over an, where the an's are the whole terms, so we include the x's. So, this is just going to be x to the n plus 1 over n plus 1 factorial times flip an upside down, n factorial over x to the n equals lim n goes to infinity. Now let's see what cancellations we get. Well, the x to the n is going to cancel with the x to the n plus 1 up top. And now we need to see how the factorials cancel. But remember what was factorial defined to be. So n factorial is n times n minus 1 times all the way down to 1. So then n plus 1 factorial is n plus 1 times n minus 1 all the way down to 1. Okay, so most of these terms, except for one, cancel. The 1's cancel, the n minus 1's cancel, n's cancel. And we're just left with the n plus 1 on the bottom. So we get lim, n goes to infinity, x over n plus 1 in absolute values. Okay, but for any fixed x, this is equal to 0. Which is always less than 1. This is for all x element of R. So no matter what x we plug in, we get by the ratio test that this series converges. So hence, R equals infinity, and the interval of convergence is the entire real line. Okay, let's move on to the second part, this important result. So, as for all x, this series converges by the first part. We have by the divergence test. So by the divergence test, that the terms have to go to 0. So it says that the limit as n goes to infinity of x to the n over n factorial has to go to 0 for all x, which implies that the limit of the absolute values of these terms goes to 0, because if they go to 0, then their absolute values go to 0. Okay, so the next part asks us to use L'Hopital's rule to show that for any given value of x, this limit identity is true. So first I'm going to define am to be the object we're limiting, so 1 plus x over m to the power of m. And we'll find that if we define cm to be the natural log of am, which is equal to ln of 1 plus x over m to the power of m. Using the law of logs, I can bring down that m. And then 1 plus x over m. And now, using an algebra trick, I'm going to write the m out front as dividing by 1 over m. And I find that limiting this is going to be easier. So let's take the limit as m goes to infinity of cm. This is equal to lim m goes to infinity of ln 1 plus x over m over 1 over m. Both top and bottom go to 0, and that's why I've written it in this form, so I can use L'Hopital. Equals lim m goes to infinity, differentiate the top with respect to m. You're considering m now to be a real variable rather than going through the natural numbers, but the function still makes sense for real m, positive real m. So if we differentiate the top, we get this, and if we differentiate the bottom, we'll get minus 1 over m squared. So we're going to get this cancellation. The minus x over m squared will cancel with the minus 1 over m squared, and we'll just be left with x on the top. So this is lim m goes to infinity, x over 1 plus x over m. Now, if we limit m to infinity, that 1 over 1 plus x over m is just going to go to 1. So we'll get x over 1 is just x. Now, how can I use this to establish the equality I was asked for? Well, I can say, so hence, lim m goes to infinity. Now I'm going to limit am. So 1 plus x over m to the m is equal to lim m goes to infinity. I call that am. Now if cm was ln am, then am is e to the cm. Now, using continuity, I can bring that limit up to the top, and this is going to be e to the limit as m goes to infinity of cm, which is e to the x. Okay, so we've established the equality that we were asked for. Okay, so if you're following the printed version of the notes, I'm going to change part 2 slightly to verify by using the binomial theorem. That the following equation holds. 1 plus x over m to the m is equal to sum k goes from 0 to m of m factorial over m minus k factorial times 1 over m to the k times x to the k over k factorial. Okay, so this amounts to literally just plugging into the binomial theorem. There's not much else involved. So here our a is 1 and our b is x over m, so using the binomial theorem, this is equal to, by definition of the binomial theorem, or by the equation we get from the binomial theorem, m choose k, 1 to the m minus k, x over m to the k. The 1 to the m minus k just turns to 1, so we ignore it. Expressing m choose k in terms of factorials, we get this. X to the k over m to the k. K again goes from 0 to m. Then grouping everything just so it looks like how we want it to look. K equals 0 up to m factorial over m minus k factorial, m to the k times x to the k over k factorial. And we're done. Okay, now on to part 3. The part 2 and 3 that I have here are equivalent to what is in the notes. They're just written in slightly different forms. So verify that the limit as m goes to infinity of this object m factorial over m minus k factorial, m to the power of k, equals 1 for all 0 less than or equal to k less than or equal to m. Okay, solution. So this just involves, the hard part about this is just recognizing how the factorials cancel. So then m goes to infinity, m minus k factorial, m to the k under m factorial equals the limit. Now let's write out m factorial. That'll be m times m minus 1 times dot 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 m minus k minus 1 times m minus k, assuming again that k is less than or equal to m, dot 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 1 all divided by m minus k factorial. Now remember, if k is equal to m, then this is just 0 factorial, so we're fine, because 0 factorial is 1. Now we see that this piece that I've highlighted is m minus k factorial. So this piece cancels with the m minus k factorial that we have in the bottom. And we're just left with lim, m goes to infinity. And now it looks like the part 3 that's in the typed notes. So all the way down to m minus k minus 1 all over m to the k, which is just m times itself, k times. And the thing to notice now is that there are k things on the top and k things on the bottom. So k terms and k terms. So divide each m on the bottom into one of the factors individually. So divide the first m on the bottom into the first m on the top, we just get 1. Divide the m on the bottom into the m minus 1, and we get 1 minus 1 over m. All the way down to 1 minus k minus 1 over m. And each one of these individually limits to 1, so the product limits to 1. And we get exactly what we were asked to prove. Now let's group all this information together, part 1, 2, and 3, to solve part 4. So in part 1, we showed that e to the x was equal to this limit, which we expanded using the binomial theorem. In part 2, to give us this limit, m factorial over m minus k factorial, m to the k times x to the k over k factorial. Now this is equal to, well, we can just change the sum to an infinite sum. K goes from 0 to infinity, and limit what's inside. Now this is not an obvious fact, but it is true that we can just extend the limit at the sum at the start going from 0 to infinity, and we preserve the equality. Again, this is not obvious, but it is true. This is equal to, by part 3, that limit I have in brackets is just 1. So this is k goes from 0 to infinity, 1 times x to the k over k factorial, which is just equal to sum k equals 0 to infinity, x to the k over k factorial. Okay, so we've established the equality that we want. Now this is a very famous equality. The x is equal to this power series representation, and as we showed in part A, the radius of convergence of this power series is infinite. So E can be expanded on all of R in this power series. Okay, so on to the next example. Consider the power series, sum n goes from 0 to infinity, minus 1 to the n, x to the n over 2n plus 1. So again, we're asked to use the ratio test to determine the radius of convergence, so we're going to look at this limit, an plus 1 over an. So up here, I'm just going to write out what an is for a fixed x, minus 1 to the n, x to the n over 2n plus 1. And I'm going to give a formula for an plus 1 under this, which is just going to be minus 1 to the n plus 1, x to the n plus 1 over, and then if I plug in n plus 1 into the bottom, I actually get 2n plus 3. Okay, so this is equal to, then n goes to infinity, minus 1 to the n plus 1, x to the n plus 1, all over 2n plus 3, times flip an upside down, 2n plus 1 over minus 1 to the n, x to the n, take the absolute value. What cancellations do I get? The minus 1s, I don't care because I'm taking an absolute value, and the x's, I'll get a cancellation there. So this is equal to, then n goes to infinity, absolute value of x times absolute value of 2n plus 1 over 2n plus 3. But 2n plus 1 over 2n plus 3 goes to 1. So this is equal to absolute value of x times 1, which is the absolute value of x, i.e. L is less than 1 if and only if absolute value of x is less than 1. So that tells us that the radius of convergence is 1. The radius of convergence around 0. Okay, so what are the endpoints? Well, if we're around 0, then it's just plus or minus 1. We can go one to the right, one to the left. Okay, so check the corresponding series for x equals to 1. So just plug in x is 1, and that x to the n will disappear. And we'll just get sum from 0 to infinity, minus 1 to the n, over 2 to the n plus 1. Okay, then for x equals minus 1, the x to the n will now be minus 1 to the n. So it's a sum from 0 to infinity, minus 1 to the n, times minus 1 to the n, which will cancel for all n. Minus 1 to the n times minus 1 to the n is just 1. So this is sum from 0 to infinity of 1 over 2n plus 1. Okay, and as the question says, we don't yet have the tools to determine whether these series converge or diverge, but we'll develop them at a later lecture. Next example, sum n equals 0 to infinity, n times 2x minus 1 to the n over 5 to the n. Again, we're asked for radius and interval of convergence. So, write down an plus 1, replacing all the n's with n plus 1's. You get the following formulas over 5 to the n plus 1. Okay, Okay, we're asked to look at their limit. So L equals, well, we're going to use the ratio test. So L is the limit n goes to infinity, an plus 1 over an, which equals lim n goes to infinity, absolute value of n plus 1, 2x minus 1 to the n plus 1, all over 5 to the n plus 1, times, flip an upside down, n times 2x minus 1 to the n under 5 to the n. Okay, so what cancellations do we get? We can cancel the 2x minus 1 to the n with the 2x minus 1 to the n plus 1, and similarly with the 5 to the n and 5 to the n plus 1. And we're just left with the limit of absolute value of n plus 1 over n times 2x minus 1 over 5. So the n plus 1 over n is just going to go to 1, so we'll get this. And that tells us L is less than 1, if and only if 2x minus 1 is less than 5. Just bringing the 5 up. And that's the same as x minus a half being less than 5 over 2. So to draw this interval, we have a half at the center, and we go 5 over 2 to the right, and we land at 3. We go 5 over 2 to the left, and we'll get to minus 2. So check the boundary cases. So x equals 3. This would be sum n goes from 0 to infinity of plug in 3. So n times 6 minus 1 to the n over 5 to the n equals sum. Well, 6 minus 1 to the n is just 5 to the n, so just to write that out, we'll have n times 5 to the n over 5 to the n. These 5 to the n's will cancel, and we'll just get sum n equals 0 to infinity of n, which is just 0 plus 1 plus 2 plus 3 and so on, which obviously diverges. Checking the next boundary case, x is equal to minus 2. Sum n goes from 0 to infinity, n times minus 4 minus 1 to the n all over 5 to the n. Minus 4 minus 1 is minus 5, so this is going to be minus 5 to the n. So sum from 0 to infinity, n times minus 5 to the n. And the minus 5 to the n will cancel with the 5 to the n and leave you with minus 1 to the n times n, which is minus 1 plus 2 minus 3 and so on. And we can see that this will never settle, so this diverges. So the interval of convergence is going to be the open interval without either endpoint. And just to highlight back up here, the radius of convergence, this tells us that the radius of convergence around a half is 5 over 2. So we found the radius of convergence and we found the interval of convergence. Okay, so just collecting what we've established in this lecture back into the table that we had in the other power series lecture, we now have this representation for e to the x. And we know that it's valid on the entire real line. So let's look at some applications of the new representation that we have for e to the x. So the first question asks us to use the method of substitution to give a power series representation for e to the x squared. So recall the representation we had for e, which was e to the x is x to the k factorial in a sum. Now I didn't have to use x, I could have easily used w. So k is 0 to infinity, w to the k over k factorial. And remember, this representation is valid for all of R. So whatever you want to plug in, you just replace. So if it's e to the w, it's w to the k. If it's e to the x, it's x to the k. So here, sum from 0 to infinity, it's going to be x squared, all to the k, over k factorial, which, just multiplying the powers, k goes from 0 to infinity, is x to the 2k over k factorial. Okay, so the second part, part B, is to use the method of integration to derive a power series representation for this integral e to the x squared dx. So let's go ahead and do that. Integral sum x to the 2k over k factorial, k goes from 0 to infinity dx. And remember our theorem about integrating power series inside the radius of convergence. You just integrate term by term. So this is sum from 0 to infinity, x to the 2k plus 1 over 2k plus 1 times k factorial. Okay, now this might seem routine and you're just going through the steps, but this is actually very impressive because this is an extremely hard function to integrate using the methods that we know. Okay, so the last application asks us to use the power series to find this limit. So you might think, looking at this, that you can use L'Hopital, but if you're to use L'Hopital, notice that you'll have to apply it 4 times, so this will get very messy. So let's see if we can use power series to make this a bit simpler. Okay, so recall the expansion we had for e to the x squared. You can write this as limit x goes to 0 of sum k 0 to infinity x to the 2k over k factorial minus 1 minus x squared over x to the 4. Okay, so expand out the sum we have on the top in the dot 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 notation. So this would be 1 plus x squared plus x to the 4 over 2 factorial plus x to the 6 over 3 factorial and so on, minus 1 minus x squared. Now, as this is a convergent series, I can cancel these terms. So I can cancel this minus 1. So I can cancel this minus 1 with this 1. I can cancel this x squared with this x squared. And I'm left with limit x to the 4 over 2 factorial plus x to the 6 over 3 factorial plus the next term would be x to the 8 over 4 factorial plus dot dot dot, all divided by x to the 4. Now, x to the 4 will divide into this. We'll kill this x to the 4, it'll leave a 2 once we divide into the x to the 6, and it'll leave an x to the 4 once we divide into the x to the 8. So this is lim x goes to 0 of 1 over 2, which 2 is 2 factorial, plus x squared over 3 factorial, plus x to the 4 over 4 factorial, and so on. Now notice if x goes to 0, this goes to 0, this goes to 0, and all of the rest of them go to 0. The only thing that survives is the half. Okay, so this was a lot quicker than applying L'Hopital's rule 4 times and a lot less messy. Okay, so this is another application of power series.